All right, good morning, everyone. I think we'll get started. Um, so, just one reminder before we get started. For homework number 7, that's due tomorrow. Okay, so due tomorrow at midnight. So it's just one day, a little bit over one day from now. Okay, and again, if you need help, I have office hours this afternoon and then early tomorrow morning. Okay, and then you can also get help from Kayla. Okay, so we'll get started. Today we'll be looking into chapter 23 here, induction, electromagnetic induction. Okay, so basically, this is the graded application of magnetic introduction is for the electric generator. So these days we see new kind of generator like wind turbine, which is clean energy. Okay, and then traditionally we use like the steam generators, like you heat the water and then the steam will drive the turbine in that case to generate electricity. And then also another form of generator is hydro electricity, which use the um, gravitational potential from the water that to drive the turbine. Okay, so um, I think we will take a look with one actually demo here, Friday's experiment. Okay, so we'll take a look with that one here. So I'm going to play a video here on this.
Electromagnetic induction. Prepare a circular coil out of copper wire. Connect the two ends of this coil to the two terminals of a sensitive galvanometer with a scale having 0 at the center. This closed circuit is shown in the diagram. Note that this circuit contains no source of electricity and the galvanometer shows 0 reading initially. Take a bar magnet NS and move it swiftly towards the coil with its north pole facing the coil. You will observe a deflection in the galvanometer when the magnet is moving. The deflection indicates that current is set up in the coil. Now, move the magnet away from the coil. The galvanometer shows again a deflection, but in the opposite direction. This means current is set up in the opposite direction. If you hold the magnet with its south pole facing the coil and repeat the above steps, the deflections are again observed, but are reversed. Similarly, motion of the coil itself also produces deflections in the galvanometer when the magnet is kept stationary. Do you observe any deflection when you just hold the magnet stationary near the coil at rest? No. A relative motion of a magnet and a coil induces the current in the coil. The current produced by a relative motion of the coil or the magnet is called an induced current and is said to be set up by an induced electromotive force, EMF. The production of an induced EMF in a coil in a closed circuit by the relative motion of a magnet and its coil is called the phenomenon of electromagnetic induction.
All right. All right, so normally if we are in class, I can show you this as well, but basically you would have a solenoid. It's like many loops of coils stacking together, and then I would put a magnet bar over there. So if I move my bar of magnetic in and out of the center of this solenoid, then you'll see on the galvanometer the needle will be deflected. Okay, so that indicates there's current induced in the coil if there's relative movement of the magnetic bar with the coil. Okay, so as the video show, this is called the electromagnetic induction. Similarly, you can do another experiment if you have coils that you actually put it into a circuit that is in series with a resistor and then powered by a battery or a power source. In that case, and then if you have a metal bar go through this coil where Another coil is on the other end of metal bar over here, with the metal bar goes through the center of that secondary coil. And if the two terminals of the coils are connected to a galvanometer, then as you can see, the moment you turn on the switch on the primary circuit here, we call it primary circuit, you'll see then the needle here on the secondary coil, secondary circuit, the galvanometer needle will be deflected if you turn on the switch, okay? But then shortly after you turn on the switch, the needle will go back to zero. And if you open the switch, you will see the needle will be on the galvanometer on the secondary circuit will be deflected again, okay, to a different, the other side of the scale. Then shortly after, you'll return to zero, okay? So both demonstration will show you that there's electric current induced in the coil. In this case, on the figure right figure here is the secondary coil. In the first figure here will be just the coil itself, okay? All right. So basically, if we summarize what we observe in the right figure above in the previous slides, then the current in the secondary coil is zero, as long as the current in the primary circuit is not changing. So if you have closed the switch for say a couple of seconds, that's considered long enough already, then the needle will stay in the center. Okay, as long as there's no change in current in the circuit, the needle will not change. And the current flows in the secondary circuit while the current is in the primary circuit is changing. So that means if you just close the switch, then the current is building up in the primary, or if you just turn it off, then the current dies out in that case, okay? So the current flows in opposite direction depending on whether the magnetic field is increasing or decreasing, okay? So if you have increasing current in the primary circuit, then the magnetic field induced by the primary coil actually is increasing, okay? And then that goes to the secondary coil. And then vice versa, if you have current decreasing, the magnetic field produced by primary coil will be decreasing, okay? The magnitude of the induced current is proportional to the rate at which magnetic field is changing. Okay, so this is the key here. It's not simply proportional to just the changing of it, but it's rather proportional to the rate at which the magnetic field is changing, or in other words, at the rate which the current is changing. Okay. And in the left figure here, you can actually break down the movement of your bar relative to the coil. So if you have the bar magnetic go into there, so then your needle deflect into one direction, but if you pull it out, then needle will be deflect into the other direction, okay? And then the current induced there, actually you can see depending on the terminals, okay, on the galvanometer, so you can tell which direction is current moving, okay? So, and then if you flip the poles of the bar magnetic, then it's the other way around, okay? And then if you have your bar magnetic stationary, then there's would be no induced current in the coil in that sense. All right, so basically, how much current is induced, or we can put it in another way, because current is proportional, directly proportional to the potential that is induced. Okay, we call it induced EMF, electromotive force. Okay, remember electromotive force is referring to potential. Okay, so how much current or EMF is induced depends on this quantity we call magnetic flux. Okay, so this is similar to the definition of electric flux. This flux is equal to the magnetic field in this case, cosine theta times A, okay, or B times A times cosine theta. So the theta, the B is the magnetic field, A is the area. So if you have a coil, circular coil, then that refers to the circular area of the circle. If you have a rectangle or square circuit coil, then or loop, then that refers to the area of that rectangle or square. the theta is the angle between the normal direction of the loop and the direction of the B field, the magnetic field. Okay, so this is called magnetic flux, right? So in that sense, any change in magnetic flux that will induce an EMF in the coil, okay, or in the loop. So you can achieve this in different ways. One is to increase or decrease the magnetic field, right? And the other way is to either increase or decrease the area of your coil. And the third way is to change the angle between the normal direction of the loop and the direction of the magnetic field. So either way, okay, so you can like any of these three ways, you can actually induce EMF. Okay, all right. So let's take a look on the definition for magnetic field, magnetic flux over here. So it said a magnetic field is orientated at the angle of 67 degree to the normal of a rectangular area 5.9 centimeter by 7.8 centimeter. If the magnetic flux through this surface has a magnitude of 4.8 times 10 to the minus 5 Tesla times meter square. What's the strength of the magnetic field? Okay, so it gives you magnetic flux. It gives you pretty much the area. It gives the dimension for the rectangular. So you can calculate what's the area of the rectangular. It gives you the angle, theta. So you can solve for your magnetic field B. Okay, so basically the equation you are going to use is the flux equals to B times A times cosine of the angle. Or theta. Let's use theta. Dang it. Yeah, should be using theta here because then if we use phi, that's the same symbol for the flux. Okay, that will cause a lot of confusion there. All right, you guys can. I think you guys can take a quick like a temp on this one, and then we can take a look on this in a couple of minutes together. Okay. All right, so let's take a look here together. So we are given the flux, we are given the pretty much the area, we are given the angle theta. So theta, it says it gives the angle of between the normal and the magnetic field. So that's the theta. Okay, so if you are given like say the angle between the magnetic field and the rectangular, then you want to do 90 degree minus the angle. Okay, but this case it's directly the angle. So you're looking for B field. So you just rearrange the terms to just have B in one side of equation and then the rest to the other side of equation. Okay. Um, so flux is given as 4.8 times 10 to the minus 5 Tesla times meter square divided by the area. You want to calculate the area. So 5.9 times 7.8. They are in centimeters. So that means it's 10 to the minus 4. Okay, meter square. Because both are in centimeter, that means you want to multiply both by 10 to the negative 2, which add up to be 10 to the negative 4. And then cosine of 67 degrees here. Okay, so then if you plug in your numbers correctly into the calculator, it will be 0.027 in Tesla. Okay, that should be what you get. Any questions you guys might have on this one? Okay, so if not, we then can move on. So as I mentioned, your induced current or your induced potential, induced EMF, is directly related to the flux changing. So then this is actually given by Faraday's law of induction, or called Lenz's law. So it says an EMF, so induced potential, an EMF is induced only when the magnetic flux through a loop changes with time. Okay, so if you have no change in the magnetic flux, then there will be no induced EMF. So basically, so this induced EMF, epsilon EMF equals to minus M. So N is referring to the number of coils you have or number of loops you have. Times delta phi. So this is change in flux over change in time t. So this is the rate of flux changing. Okay, you can do minus of N flux final minus flux initial divided by T final minus T initial. Okay. All right. So that's the equation you can use to calculate the induced EMF. Okay. All right. So in our daily life, there's actually many applications of the induced EMF. Okay. So one application will be the guitar pickup, and also for the microphones. So how it works. So I'm going to just briefly introduce how this is both in two cases, how they are working, and then we'll take a look on a demo video on guitar pickup. Okay, so basically if you have a pickup over here, guitar pickup over here, so inside the pickup there's this pickup coil we call it, and then there's this permanent magnetic. Okay, so with not the north pole and south pole, and then the part of the string that is close to the pickup, it actually has a small piece of magnetic over there. Okay, so as you plug your guitar string, this guy moves back and forth, back and forth. So then that will push this magnet back and forth, because the two will have interaction. So like poles will attract each other, and then opposite pole will repel each other. But basically, it's having interaction over here, so makes this guy go back and forth, back and forth. Then that induces the motion of the biomagnet here with your coil over here. So then there will be induced EMF in this coil. Okay, send it to the amplifier that carries the frequency of your guitar string, which determines the tune of the guitar string and be amplified. Okay. For the microphone, the way it works is there's this diaphragm. So when the sound wave hits this guy, then it moves this, push this guy back and forth, back and forth. Okay, now this biomagnetic field, magnetic, it's stationary in this case. However, now you have the coil move relative to the this guy. So then there will be flux, magnetic flux changing here. Okay, so similarly to this side, there will be magnetic flux changing if this magnet is going back and forth. Okay, now this guy, in this time, the coil is going back and forth. Okay, so then that is pick up with the microphone to the amplifier. Okay, all right. So let's take a look on this video here. It has more detailed explanation of how a guitar pickup is working.
Rock and roll. This is a pickup coil from an electric guitar. And I hope that you can see that there are 1, 2, 3, 4, 5, 6 magnets right here. Let's prove that they're magnets. Yep, stuff sticks to them. And each magnet is designed to magnetize a string of the guitar. So the strings will be like, well, the pickup would be like that if the strings were like this, doom, 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 in front of it, and you go like that, and it would be awesome. Or we could show it like this, and I think that might make the most sense. This coil here has 500 or so turns. Wow, that's a lot of turns. What is this pen thing? Okay, here, let's get a marker here. We're talking about 500 turns or more. And out of this just comes 2 wires. So let's talk about how rock and roll is made. I'm gonna zoom in on just one of these magnets. The magnet's like this, and it has a north pole and a south pole. I don't actually know if the north pole is the one that's sticking up, and I frankly don't really care. But there is a coil going around it like this. Lots and lots of turns. Hundreds of turns, and the coil comes out and goes out, and yeah, so it's got 2 leads leading from it. But in front of the magnet lies a string, and from our perspective, the guitar string is sliced and would appear right there. I guess it's gonna be a little bit smaller, but I wanted to show you that when the string is nearby the magnet, then the string becomes magnetized, and you can bet that it would prefer to have this side be south and that side be north, assuming it's a ferrous material. So we're going to set it up like this, and then if you hit the string, boom, you hit the string, that string will shake back and forth, which in turn will change the amount of flux going through this coil. Now, does this coil like having its flux change? But the coil is monitoring the change in flux at every instant. So it's getting this derivative of the flux as a function of time, and it's multiplying that by the number of turns that we've got. So this is a big deal, and then putting a minus sign on it to find the induced voltage on the coil. So the coil is spitting out a...
So I'm pausing this briefly. On the sign here, it says, he says derivative of the flux over derivative of time. So that's basically the change of flux over change of time, okay? If you approach your change in time to 0, then that's doing derivative, okay? So next time you see a derivative, don't be scared by the symbols. That simply means change in flux over change in time, t, okay? But that's with small change, okay? So let's resume here.
Voltage function that's sometimes big and sometimes small and sometimes big and sometimes small as the string is vibrating up and down. And we're probably going to get a graph that looks kind of like this. V induced as a function of time will be like this, and the frequency, well, this is like a period or something, and 1 over that would probably be the frequency, but the frequency will correspond to and be exactly the frequency of the vibrating guitar string. So the information about how the guitar string is vibrating is carried in the induced voltage. And this is awesome because now you can amplify this and send it around, and then you can then hear the movement of the guitar string without having to have any sound come from the guitar string and be amplified through the body of the guitar and then come to your ears. So it could just be immediately recorded, or it could be amplified and then played back on speakers, etc. So let's make a little schematic diagram of what we've got. we've got a guitar. And I suppose it has to be an electric guitar. And then we can send the signal from the guitar to some pedals, and those pedals can change the sound in a lot of awesome ways. I'm only beginning to explore that. You probably know more than I do about it. And then we'll go to an amplifier. So you're talking about Fender or Marshall or something. And these guys are going to make your sound louder. Not your sound, I should say your signal. So they're going to take a small induced voltage, and even though there are 500 turns or so here, we're going to say that this voltage is rather small, probably in the millivolt range. And they're going to make it in the volt range. They'll make a much, much larger voltage change coming out of that sucker, coming out of the amplifier. Then the amplifier will send the signal to a speaker. If it's not being recorded, it's going to be sent to a speaker. We'll talk about speakers in just a minute. But before we talk about speakers, I want to ask you a couple questions about guitar. For instance, would it work with nylon strings? Electric guitar with nylon.
I think we can stop over here. That explains how the guitar pickup works. Okay, so for nylon, it will not work because it will not be magnetized, so then it will not pick up. Okay, so we'll skip that. All right. Okay. Any questions you guys might have at this point? All right, if not, we are going to take a look on one example here. So this is basically applying Lenz's law. So it says a single conducting loop of wire has an area of 7.2 times 10 to the negative 2 meters square and a resistance of 110 ohms. Perpendicular to the plane of the loop is a magnetic field of strength 0.88 Tesla. At what rate in T per second must this field change? Okay, so that's change in rate. If the induced current in the loop is to be 0.43 amps. All right. So I think I can give you guys a couple of minutes to think about how you want to solve for this, and then we can take a solution together after that. Okay. All right, so let's take a look here. It says a single conducting loop. Okay, so we can apply Lenz's law here. Induced EMF, or the voltage induced, is equal to minus of m delta phi over delta t. Okay, in this case, it says just one single loop, so m is equal to 1. All right, and it says it has an area of 7.2 times 10 to the negative 2 meters squared, and resistance of 110 ohms. Okay, so perpendicular to loop, so you can see there's the loop here. Okay, itself has, you can say there's two terminals out of this loop. Itself has a resistance of 110, and the area is given that. Okay, so it says perpendicular to this loop, so this guy, there's a B field. Okay, the B field is given, all right, 0.88 Tesla. Okay, so this is the initial. Okay, so I can say B initial. Right. So it's asking you at what rate must this field be changing? So then the induced current I is equal to 0.438. So it's looking for the change of B field at the rate. So that means delta B over delta T. Okay, what's that change? All right. So let's take a look here. So it tells us the current. All right, it tells us the resistance of this. So then according to Ohm's law, I think we can calculate what's the induced EMF over here, right? So induced voltage, this is the voltage. The voltage should be equal to then I times R, okay? This is according to Ohm's law. Now the phi for the magnetic flux, this is equal to B times A times cosine of theta. In this case, the B field is in the vertical direction of this circle. So that means the theta is equal to 0, okay? When you have theta equals to 0, cosine of theta is actually equal to 1, okay? Sine of 0 is 0, cosine of 0 is actually 1. So this is 1, okay? So phi equals to B times A then, okay? Now, then delta phi would be equal to delta of B times A, okay? The change of these two multiply. Now, area is not changing, right? Because in this problem, it tells you that the magnetic field will be changing, the area is not. So then that's just equal to the change in the B field times A, okay? A is not changing. So then you can actually write that the induced EMF is minus of delta phi, which is delta B times A divided by delta T, okay? And this is equal to I times R. You can calculate that, or you can keep replace epsilon with I times R. That will be equal to minus of delta B over delta T times A, okay? All right, so I think in that sense, now we have everything we needed because we are looking for this guy, delta B over delta T. Then we can move this to the other side of the equation. So delta B over delta T then is equal to I times R divided by A, right, with a negative sign, okay? Now, when you're looking for a rate that is changing, so it's actually just care about the magnitude of the rate of changing. So you can forget about the negative sign, or you can take absolute value of it, okay? So in this case, you can plug in your numbers. I is 0.43 amps. The R is 110 ohms, and divided by 0.4, no, 7.2, sorry. 7.2 times 10 to the minus 2 meters squared, okay? So then your delta B over delta T, or let's say we are just looking at the absolute value of it, that should be equal to, after all this, should be equal to 6.6 times 10 to the second Tesla over second. Okay, that's at what rate that this field must be changing. Okay. Questions you guys might have on this one? Yeah, unmute yourself and speak up if you do. Okay. All right, if we are clear, so then let's take a closer look on Lenz's law. So it says, so there's a negative sign when we take a look on Lenz's law, epsilon equal to minus, okay? So that minus come from if you have an induced current, okay? So then it always flows in the direction that opposes the change that occurs it, okay? So that's because of that, so we have a negative sign. So let's take a look over here. So if you have a coil over here, now you have a bar magnetic. If you're approaching your bar magnetic towards it, okay. So then there will be induced current in this coil over here. So we know that if you have a current carrying coil, then there's a magnetic field will be produced by that current, right? So in that case, then you can see if this bar magnet is moving towards the loop, okay? So then the loop will, because of the current that induced, will produce a magnetic field that is opposite to this guy if this is moving, because the like poles will be repulsive to each other. Okay, so then that's repelling it. Actually, it's opposes that by going close. So you'll probably see a repulsive force if you are doing that. So in that case, you can use your right hand rule. So your thumb goes in the direction of the current, then the four fingers are in the direction of your induced magnetic field. So the magnetic field is pointing towards the north pole of it. So then it's in that direction. Okay, opposite to this direction. Okay, now on the other hand, if you pull this guy away from it, then this induced magnetic field should be opposes that motion. So then it will produce a magnetic field that is opposite to this guy. So then you will have opposite poles close to each other. So then there will be attractive force towards the loop there. Okay. All right. So in that sense, for Lenz's law, if you have the magnetic field that is increasing inside this loop, then the magnetic field created by the induced current will be in the opposite direction. Okay. So if decreasing, then it will be in the same direction. Okay. So just remember, if you have increased magnetic field, then the induced magnetic field will be in opposite to that. Okay, if the other way around, then it will be decreased. Okay, so that's basically Lenz's rule, and then that's where the negative sign from the equation is from. All right. A few more examples here. So if you have this guy going towards this coils over here, all right? So you can see then induced B field will be in the opposite direction of that because this is now going into it. So then it will repel each other, okay? So in that sense, you can then determine what will be the induced current in that case, okay? Use your right hand rule for that. All right, so you put your right hand up, your four fingers curls in that direction. Okay, so then the magnetic field will be in this direction. If you pull this away, then it's the other way around. Okay, and then if you flip the pull, then again it's another way around, the other way around with the first example over there. Okay, so you want to probably get some more practice on your right hand rule here. All right. Next, we'll also look at what's the some more application of this induced current. So we have been looking at the loops, but however, if you have a piece of metal piece like a rectangular shape like this, okay, if you have it goes through the magnetic field like this, all right, then actually it will induce a current inside the sheet of metal in a circular form. This is called the eddy current, okay. And if you have this guy, for example, it's pulled by the gravitational force going downward, so then this induced current will oppose to that. So the effect of this induced current, because you have magnetic field, then there's a current, so then there will be interaction with the field and the current. So then the force will be in the opposite direction of this guy. Okay. So then if you have a sheet of metal and then a sheet of say insulator, you will see that when you release them, both of them inside the magnetic field, you will see that for metal, it will actually go slower than non-metal. Okay, so non-metal will go faster because it's purely the gravitational force. This is there's a opposite force produced due to the eddy current, okay, inside the field. Okay. And the drag the eddy current produces is called the magnetic damping. Okay, so one application would be the electric brake. So then when that is applied, so then current is sending through coils on the two sides of this metal drum, so that will produce a magnetic field. Okay, so then in that sense, this is magnetic field, this is moving inside the magnetic field, so then eddy current will be produced on the drum over here, then that will produce a drag force on the rotation of this drum, so then that slows down the wheel. Okay, in that sense. Another application would be if you have a piece of metal, you can have it go through this magnetic field over here. So then the oscillation will be damped quickly. Now, if you have small slices on the sheet here, then actually there will be still eddy current produced, but much smaller. So they largely cancel out each other. Okay, so then in this sense, it will not be affected too much. Okay. Now, if you have non-conducting material as the sheet, then it's not going to be affected either, okay? That's the third case, part C in figure C there. So basically, when that happens, if you have a metal sheet here, eddy current will be in this direction, and then motion is in this direction, so the drag force will be in the opposite direction of the motion, okay? So then we will damp it down quickly, okay? Due to the presence of the magnetic field there. You can use your right hand rule to determine the direction of the force, okay, or the current, okay, because the force is always opposite to the motion. So in that sense, the direction of the force is known. You can use that to determine the current, direction of the current. All right. So if you have like openings like that, so many small eddy currents will be produced, and then from this one to that one will be canceling out each other. Okay. So then the net effect is much smaller. Also, this eddy current can be applied to if you are sorting like garbages. If you want to have the metal pieces separate out from the non-metals, so then basically there's a big magnet over here. You put the garbage going sliding down here, so then the metal piece will be dragged. That's due to eddy current because of the motion over there. Okay, non-metals will move on. Also, metal detectors that works the same. So then there's magnetic field produced by this guy. If you sweep it back and forth, then the metal piece, if there's a metal piece underground, then it will have a drag force on this guy. Okay, so then it will pick up that drag signal over there. All right. Any questions you guys have on eddy current before we move on to the next section? Okay, so if not, then let's move on here. So I think in the previous example, when we take a look here, we actually have changing magnetic field, and then we're calculating for that changing magnetic field. Okay. However, when we take a look on the flux equation, it says flux equal to B times A times cosine of theta, right? So you can change magnetic field to have the change in flux. You can also actually change the area of your loop to have the flux change. So in this case, in the figure over shows over here, so if you have two metal rails or conducting rails, and then there's a resistor connect to it, and then this is also a conducting rod. Okay, so if you have a rod that is sliding along these two rails, then the loop that the resistor, the rail, and the rod make, okay, so will be changing. So then that means the area of the loop is changing, okay, with time t. So if that's the case, then flux will be changing due to the changing of the area of the loop, okay. So if area is changing, then you'll have flux changing. Then you will have induced current or induced EMF through this rod, okay. So for that, we call it as motional EMF because then there's motion of this rod. Okay, so if your rod moving, and then the rod completes a circuit, a circle with other elements, so then the area is changing. So in this case, you can calculate what's changing in delta A. All right, the magnetic field B is the same, so B times delta A. Now in this case, the magnetic field is perpendicular to the loop here. So the theta is equal to 0. So cosine 0 is 1. So it's just B, flux is just B times A. And then change in flux delta phi will be just corresponding to change of A, then times B. B is not changing. Okay, so you can calculate what's changing in A. That will be L times delta X. Okay. Let me just probably just derive this for you guys. You can have the slides open, but basically because flux is equal to B times A times cosine of theta, in this case, theta is 0 because the magnetic field is perpendicular to the loop, okay? So then change in flux should be just equal to B times change in the area. And this is 1, okay? And epsilon equal to minus n delta phi over delta t according to Lenz's law. So then this is equal to minus of, in this case, we'll be just looking at one loop, okay? So minus of 1 times delta phi will be b times delta a over delta t, okay? So b is not changing, okay? So delta a is equal to the length of the rod L times the movement, the distance moved by the rod. We call it delta x, okay? So then this is equal to minus of b times L times delta x divided by delta t, okay? So if you have delta x divided by delta t, that gives you the speed, right? That the rod is moving, okay? So then epsilon is equal to minus bl times v, okay? If you just look at the magnitude of this, then it will be just equal to b times l times v, okay? So this will be your induced EMF, okay? So your induced EMF or motional EMF is equal to B times L times V. B is the magnetic field, L is the length of the rod, and then V is the speed at which this rod is moving. All right. Okay. And because this is induced EMF, so similarly, for the current induced, it will have the effect that is opposing to the change of the area. So the change area, so you have motion going to the right in this case, then the induced current inside the loop will produce a magnetic field that is actually opposite to the original direction of the magnetic field, because now in this case you have increase in magnetic flux. Okay, so to oppose that that increase, you want to have the flux actually reduced. So then that is by having the reduced magnetic field in the other way around. Okay, so this is the in B induced over here, which is in the opposite direction of the original magnetic field. Okay, and then in that case, you can determine what's the direction of the current. So current will be then in this direction by using your right hand rule. Your four fingers curve in the direction of the induced magnetic field, and then the thumb points in the direction of the current induced. Okay. And you can also determine what will be the force, magnetic force this guy experienced. So if you have this goes to in this direction, then the magnetic force will be in the opposite direction of it. Okay. All right. So if you have now in this case, if you have the resistor replaced by LiPo, then you'll see that if you have this rod goes to either direction, actually it doesn't matter, you will have an induced EMF. So then this will it will light up if the induced EMF is large enough, and you'll see that. Okay, so this is basically a kind of generator you could have, right? So you basically move this guy in that direction, and then because of that, you are changing the flux, magnetic flux, so then you'll have induced EMF over there. So basically, you probably will pull this, okay? So that means there's mechanical work being done, or mechanical energy is actually converted to the electrical energy over here, provided to the LiPo, right? So then that's one type of the electric generator you can design. Okay, so in this case, if we take a look, I think I just showed this on my paper over here. So the change in flux, you can calculate in this case B times A delta A, because B is not changing, and then theta is 0, so there's no cosine theta term. Delta A is equal to V times delta X, which is equal to L times delta T, okay? Or V times delta T, sorry, delta X. So then epsilon induced EMF magnitude is equal to n times delta phi over delta t, where n is equal to 1, and BLV delta t over delta t will cancel out, equals to B times V times L. Okay. Now, because there's electric potential induced inside the rod, so then on the two ends of the rod, there's electric potential difference, then you can imagine there will be electric field inside the rod, right? So electric field inside the rod should be equal to the potential epsilon divided by the length of the rod, okay? L. So if you do epsilon divided by L, then that gives you the electric field E, capital E, that's equal to B times V, okay? So the electric field caused by the motion of the rod is E equal to B times V in that case. All right. And you can calculate what's the magnetic force that the rod is experiencing if it moves in with the speed of V. So then the force, magnetic force, should be equal to the current induced times the length of it times the B field, the external B field. And for the current it induced should be equal to the epsilon divided by R. Epsilon is equal to B times V times L. Okay, so in that sense, then you can see F will be equal to, there are two B's over here, so B squared times V times L squared divided by R. Okay, so that's the force needed, or the force the rod experience. Okay, B squared V divided times L squared divided by R. And if you want to maintain the constant speed of v, then your pulling force should be also that force F, right? The magnetic force. So then the mechanical work needed is the force times v. This is what we learned in the first semester for the power of a driving force. So force times v, and then that becomes b squared v squared, because there are two v's, and L squared divided by R. Okay. On the other hand, you can also calculate what's the electric power consumed in the light bulb. So then that's equal to I squared times R. I is the epsilon divided by R. So I is epsilon is BVL divided by R. So then BVL divided by R squared times R. Okay. So then you can also figure out that's equal to B squared V squared L squared divided by R. So in this case, then mechanical power is exactly equal to the electrical power. So that's basically conservation of energy. You actually just converting mechanical power into electrical power in that sense. Okay, for your calculation, you can see those two are identical to each other. All right. So if you are pulling the draw, then basically what you are doing is converting your mechanical power to your electrical power. And then that's the fundamental principle for electricity generator. Okay, so basically it just convert energy from one form to the other form. All right, I don't think we'll have time for this example, but we'll come back on Wednesday for the example. Okay, so we'll just stop here for today and then see you guys on Wednesday for the lecture. Okay. Bye, guys.